Alright, welcome back everybody. In this video we're going to look at using the rectangular approximation methods with numerical data, and we're actually going to look at some old AP free response questions from some previous years and how rectangular approximations were used in those with numerical data. And we're looking here first at free response question number 3 from the 2010 AP Calc AB exam Form B. And let's see what we've got here. It says the figure above shows an above ground swimming pool in the shape of a cylinder with a radius of 12 feet and a height of 4 feet. The pool contains 1,000 cubic feet of water at time t equals 0. All of that's not going to be important for what we're doing in this part. During the time interval from 0 to 12 hours, water is pumped into the pool at the rate P of t cubic feet per hour. So that's what this table up here represents. It represents the rate that water is being pumped into the pool. The rest of this lead-in is for a later part of the question that we're not going to look at in this video. So part A, we're supposed to use a midpoint Riemann sum with 3 subintervals of equal length to approximate the total amount of water that was pumped into the pool. Now, one key thing for us to know here is that the total amount of water that was pumped into the pool is equal to the area under the rate curve. And so what we're going to do is we're going to use the data from the table to approximate the area underneath the rate curve, which is going to give us the total amount of water that was pumped into the pool. Now, we're told here to use a midpoint Riemann sum with 3 subintervals of equal length. So in our original problem, we've got time values running from 0 to 12. So we're going to subdivide that into 3 equal subintervals. So 12 divided by 3. Each of the subintervals that we're looking at should be 4 units wide. So we're looking at the subinterval from 0 to 4, and the subinterval from 4 to 8, and the subinterval from 8 to 12. And so in order to do this, we're going to write out our expression. The width of each rectangle we just found out is going to be 4 units wide, and they're equal subintervals, so I can factor that 4 out in front. And then I need the value of the function at the midpoint of the first subinterval. So the first subinterval is from 0 to 4. The midpoint of an interval from 0 to 4 is at 2. So we need the value of P of 2 for the height of that first rectangle. And for the second rectangle, we need P of 6, because that's the interval from 4 to 8. 6 is where the midpoint occurs. And then for the third subinterval, we need P of 10. And so we'll pull all those values from the table. P of 2 here is 46. P of 6 is 57. And P of 10 is 62. And now we'll go ahead and calculate the value here, the total amount of water. And we've got 4 times, let's see, that's 165. 4 times 165. Which should be equal to 660. And now I want some units here. This is the total amount of water that was pumped in the pool. The water's being pumped in at a rate in cubic feet per hour, so this is going to be measured in cubic feet. And there we go. We've used a midpoint Riemann sum to approximate the total amount of water that's pumped in over that 12-hour period. Alright, let's go on to example 2. This is free response question number 5 from the 2009 AP Calculus AB exam. We've got a function x and f of x that you see here. Let f be a function that's twice differentiable for all real numbers. Table above gives values of f for selected points in the closed interval. Use a left Riemann sum with subintervals indicated by the data in the table to approximate, and we've got this weird symbol that you guys haven't seen yet. This is the integral symbol, which roughly for us at this stage in our understanding means the area underneath the curve f of x from 2 to 13. And so what we're doing here is we're just going to use a left Riemann sum from this data table in order to approximate that value. This example is different from everything we've done so far in that the rectangles have different widths because we're using the subintervals indicated by the data in the table. So our first rectangle is going to be the one that goes from where x is 2 to 3, the next from 3 to 5, the next from 5 to 8, and the next from 8 to 13. And then we're just going to pull the heights from the left endpoint. So for the interval from 2 to 3, this is going to be our height, 1. For the interval from 3 to 5, we'll again use the left endpoint. For the interval from 5 to 8, we'll use the left endpoint. For the interval from 8 to 13, we'll use the left endpoint. And this right endpoint of the whole interval won't actually get used in our calculation. So our first rectangle from 2 to 3 is 1 unit wide, and the height that we're going to use is at the left endpoint, that's 1. And then the next rectangle from 3 to 5, that's a width of 2 units, and the left endpoint of that interval is 4. And then the next rectangle for the interval from 5 to 8, the width of that rectangle is 3, and the height we're going to use for that rectangle is the left endpoint, -2, and the last rectangle from 8 to 13 is 5 units wide, and we're going to use the left endpoint of that interval, which is 3, for its height. And so, doing these calculations, we've got 1 plus 8 minus 6 plus 15, and so we are going to approximate that value as 18. Alright, and on to our last example for this video, example 3. Let's see, we've got this data table. The volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function r of time t, where t is measured in minutes. The graph is concave down. That's not important to us at this moment. The table above gives selected values of the rate of change, r prime of t, of the radius over the time interval from 0 to 12. And now it says, use a right Riemann sum with the 5 subintervals indicated by the data in the table to approximate the integral from 0 to 12 of r prime of t, which is the area from 0 to 12 under the r prime of t curve. And so, we're using a right Riemann sum with the subintervals indicated by the data in the table. So, we're going to do one for from 0 to 2, a rectangle from 2 to 5, a rectangle from 5 to 7, from 7 to 11, and from 11 to 12. And for our heights, we want the right endpoint. So for the interval from 0 to 2, that's going to be our height. And for the interval from 2 to 5, that's going to be our height. Interval from 5 to 7, interval from 7 to 11, and the interval from 11 to 12. And so, for the interval from 0 to 2, the width is 2. The height is going to be 4.0. For the interval from 2 to 5, the width is 3. The height is the right endpoint. That's 2.0. From 5 to 7, the width of the interval is 2. And the height at the right endpoint is 1.2. For the interval from 7 to 11, the width is 4. And the height at the right endpoint is 0.6. And for the width from 11 to 12, the width of the interval is 1. The height at the right endpoint is 0.5. And now we're going to do all the calculations. That's going to be 8 plus 6 plus 2.4 plus 2.4 plus 0.5. We add all that together, that's 14, 16.4, 18.8, 19.3. and that's going to be measured in feet, since our rate function up here was measured in feet per minute. The area under the rate function curve is going to be measured in feet. Now, it says also in this question, using correct units, explain the meaning of the integral from 0 to 12 of r prime of t dt in terms of the radius of the balloon. And so this is the sum of the change in the radius. And so, in correct units, this means that the radius of the balloon increased 19.3 feet over the 12 minutes from t equals 0 to t equals 12 that it was inflated. And of course, your explanation does not need to be word for word what mine is, but the key components of this that you have to indicate are the value that we found with our approximation. Come on, highlighter. The value that we found with our approximation, the minutes, notice I have units for both of those, and the interval that we're talking about time-wise. Okay. That's the end of this video on RAM with numerical data. See you guys next time. Have a great rest of your day.